This video is all about solar system observation. And just with the previous videos, I'm going to show you the specification. So this is what we're going to be looking at today. Not so much in this video, so it shouldn't quite be as long. It's mainly to do with what you look at when you look up at the celestial sphere. Starting with how you can observe the sun safely, then how you can identify planets and what planets might look like in the night sky, then how we define the coordinate system for that celestial sphere that we're looking up into. And then we're going to have a look at a few things like meteor showers and these technical terms that you can see on the list there, things like conjunction, opposition, and so on. So starting with observing the sun safely, the easiest way to observe the sun safely is to use a pinhole camera, which is little more than a box with a tiny hole in it. That tiny hole lets through light, and because light travels in a straight line, the light that is emerging from up here somewhere will appear down here on a screen, and light that's emerging from down here somewhere will appear up here on a screen. Now, the smaller you make your pinhole, the crisper your image will be, the more in focus it will appear. But the less light that gets through, and so that'll make it harder to see your image. So for something like the sun, which is giving out a tremendous amount of light, pinhole cameras can be really useful. Obviously the image is upside down, but that doesn't really matter because if you use a normal regular camera to take a picture of the image from the pinhole camera, or if you place a piece of photographic film on the back of the pinhole camera and then have it developed later, you just turn the image upside down afterwards and you can see what you're looking at. Now, if the hole is too big, then the image won't be as sharp. It'll be a bit blurry around the edges. You can make a pinhole camera with a shoebox and put a small hole in the middle, and then you cover that hole in a piece of very dark tape, maybe electrical insulation tape, put a tiny, tiny pinprick through that, as small as possible. And then what you can do is on the backside of the shoebox on the inside, you can put a piece of photographic film, but be careful not to expose it to the light, otherwise it's ruined. Or the other thing you can do is cut a square at the back of the shoebox, put a piece of grease-proof paper, and then you'll need something big and heavy to put over your head when you're looking through the camera to block out all the ambient light. And then just point the pinhole camera where you want to look. And you've got to use a pinhole camera or something like that for the sun because the sun is so bright. If you look at it through a telescope, it will damage your eyes. If you look at it directly, it will damage your eyes. And there are all sorts of bizarre ideas like using CDs, compact discs, DVDs, or some other sort of makeshift filter. I wouldn't bother with any of that. You can buy some very good filters that block out ultraviolet light from the sun, and a lot are visible as well. They can be quite expensive. So a pinhole camera is usually the better option. If you just use a normal camera, it's got lenses and things like that in, you can damage the camera. And if you've got old-fashioned photographic film in the camera, it'll be overexposed and you won't see anything on any of your pictures, not just the picture of the sun, but anything else that's on that roll of film as well. And I've always enjoyed this picture here. So this is a picture of a partial eclipse, but rather than using a pinhole camera, the trees, the canopy of the trees, has provided the little pinholes for you. Those little pinpricks of light you get through in between the leaves in the trees have produced an image on the floor of the sun during this partial eclipse. And all I wouldn't say they were shadows, it's the opposite of a shadow. These curved paths you can see are images of the sun that has passed through those tiny little pinprick holes between the leaves. So that's how you observe the sun safely, and the sun can be quite easy to find in the sky, especially if there's no clouds. It's the big bright star. But what about any other celestial bodies? Maybe you're looking for planets. They're interesting to look at. Well, you'd usually look along what's called the ecliptic. And the ecliptic plane is the plane that all of the planets, including the Earth, orbit around the sun. It's in one big disk, like some sort of big pancake with a bulge in the middle, which is the sun. And around the outside on that flat pancake disk are where the planets lie. And so the sun and all the other planets will be on this disk as well from our point of view. Now, because the Earth's axis is tilted by about 23 degrees, 23.5 degrees it says in this diagram here, because of what we call that axial obliquity, the ecliptic is not in the same line in the sky as what we call the celestial equator. The celestial equator is an imaginary line across the sky that you would see if you stood on the geographic equator and looked directly up. And you know what the equator is? It's that line that runs around the middle of the Earth, equidistant from the two poles. So the celestial equator runs across the sky, but the ecliptic runs across the sky, but it's not quite in the same place, except for two locations. That's this location here, where the ecliptic and the celestial equator cross. It's an equinox. This one's the vernal or spring equinox. And this one over here, which is another equinox. This is the autumn or the September equinox. Now, basically, anything that you've got on Earth, you've got a celestial coordinate system that matches it. So we've got the celestial equator because we've got the equator on Earth. And we've got the celestial North Pole, which is directly above the geographic North Pole. And that's very close to where Polaris sits at the moment. And if you stand on the geographic South Pole and look directly up, you'll see the celestial South Pole. So just put the word celestial before it, and you've got the position in the sky above the geographic version of the same coordinate. Now, throughout history, the ecliptic plane was seen as being very special because it was on the ecliptic plane that the planets moved, and the planets were different to all the other stars. Over a long period of time, when you observe the celestial sphere, you look out into space, the constellations and the asterisms within those constellations don't appear to change over thousands and thousands of years. An asterism is what you call a group of stars that look close together in the sky. They're not necessarily close together, but they just look close together from our point of view. So that's an asterism. A constellation is a region in the sky where you find these asterisms. So the constellation of Aries, for example, has this asterism, this characteristic three little stars that you can see, which apparently is a ram. I can't see a ram in that. And Scorpius, okay, I can see that as a scorpion. I can see that one. That's the asterism within the Scorpius constellation. And there are actually 13 constellations, there's actually 13 of them, where the sun seems to pass and completely block off that particular constellation at some point during the year. At the moment, again, it does change because we have an axis that wobbles and all this sort of thing. Now, in the position you can see here, the constellation of Leo is the other side of the sun. So we wouldn't be able to see it. When we're looking in that direction, it's daytime. Can't see the stars very well during the daytime, except for one star, the sun. But you'd be able to see Aquarius and Pisces and Capricorn and Sagittarius and all those at nighttime on the other side of the Earth. And what was important is the planets seem to move relative to the background stars from one night to the next. You might see it in front of Aries, but then the next day it might be a bit further along from where it was before. And then, weeks later, it could actually be in Taurus. So this wandering star, they called planets because they were different to these stars. They wandered around. And they always seem to wander in this ecliptic. So these have got a special name. These are the zodiac signs, but we're not going to get into any nonsense like astrology here. But astrologers put special emphasis on where a planet is relative to that particular constellation and things like this. But no, we just use it as a way of breaking the sky into chunks. And you can see here all the planets are in that same ecliptic. And sometimes you get lucky. Sometimes all of the planets that are visible with the naked eye are all seen in the sky at the same time. And you've got to get lucky here because you can see the planets that are closest to the sun move faster. This isn't to scale, I should add, but it's a fair enough diagram for what I'm trying to show here. The outer planets move much slower than the inner planets. But sometimes you get lucky and the planets all line up. So when this picture was taken, you can see Mercury, Venus, Earth you can see, just look down. You can see Mars, Jupiter and Saturn. And you can't see Uranus or Neptune because you can't see those with the naked eye. But you'll notice they all go along a straight line. In fact, it's not quite a straight line because we've used a fisheye lens here, so it would look like a curved arc across the sky called the ecliptic, and that's where all the planets roughly lie on. So here's another really beautiful picture of the ecliptic, and you can see this is a planet and this is a planet, and that's probably a planet there as well, and maybe that's a planet. I mean, I'm not sure what these planets are, but you can see they all line up along that ecliptic, and from one night to the next their relative positions will move or wander around compared to the background stars. When I say wander, so here is some photographs of the night sky taken in the same patch of sky at the same time each night. And you can see there's an asterism here which should look fairly familiar to you. And you can see that these two planets seem to, from night to night, they seem to move along. And then all of a sudden they stop and turn around and go back, and then they carry on again. And this is very peculiar behaviour that you can observe when you're looking at stars over a long period of time. You notice a planet and you identify where that planet is. You make a little note of it, and one thing you can actually do is print off perhaps a star chart and mark where the planet is each night, and you can see this behaviour happening. This is called retrograde motion. Retro means backwards, so retrograde motion is where a planet appears to stop, go backwards for a bit, and then carry on. And it's caused by our point of view looking at a planet that we are undertaking, or indeed we could look at a planet undertaking us and we'd see a similar sort of effect. So the diagram on the left, the Earth is in blue, and let's say Mars is in red. And the Earth is moving faster than Mars because it's closer to the Sun. But from the Earth's point of view, we see what's on the diagram on the right. We see the Earth in the middle. We think the Sun is going around the Earth, and then we think that Mars is going around, well, the Earth as well. But you'll notice that as we get closer to Mars, we get closer to Mars in this diagram. Now, you would not be able to see Mars at this point in the year here because it would be during the daytime. So you wouldn't be able to see this part of the orbit. You'd start to see Mars perhaps here, then you'd see Mars perform this little dance where it appears to go backwards, and then it would continue, but you wouldn't be able to see it again. So here's another little animation to show you what I mean. When we say this, the planet appears to be moving, it's relative to background stars. So at this point, Earth is in green and the red is Mars. Mars appears to be in front of these particular stars. And you can see that in general, Mars appears to be moving to the right relative to the background stars. But all of a sudden, it seems to go left a little bit, and then it carries on right again. And that's what you can see on this picture on the bottom here. This retrograde motion, the prevailing motion of Mars being from left to right, but then it appears to drift to the left again as we undertake Mars. Okay, let's go back to our coordinate system for talking about different stars and planets and where they are in the sky. We've already had some points. We've had the celestial poles, the north celestial pole, the south celestial pole. We've got the ecliptic with the Zodiacal Band along that ecliptic. But there are other parts of the sky. And just like on the Earth, where if we only had the poles, the equator, and perhaps a few, sort of 12 or 13 places along the equator, we would struggle to say exactly where people are on the Earth. We like having addresses with longitudes and latitudes and all the rest of it. So we've got the same sort of thing in space, a sort of celestial longitude and latitude system. But in order to have a longitude and latitude system, you have to have a fixed point that you measure your angle around from. So on Earth, we've got the Greenwich meridian, the prime meridian, passing from the North Pole to the South Pole through Greenwich. And we can see how many degrees to the east or how many degrees to the west of the prime meridian. And then, of course, we've got the equator, and we can say how many degrees north or how many degrees south of the equator. And that's our system for longitude and latitude, and it works very well. But the Earth is rotating, so we can't really use that system where we say a star is directly over a particular part of the Earth, because that depends on what time you're looking, because the Earth is rotating. So we came up with a different system. And that is to, basically, it's copied what we had already, but we have our prime meridian for space, the celestial prime meridian, by using this one of 2 points, one of these 2 points that you can see on the diagram here. And you recognise this diagram from a previous video. So the 2 points I'm showing you here, the first point of Aries, That one is the prime meridian point. That is the middle of celestial space. It is where the sun appears to be when we are, relative to the Earth, when we are in the spring equinox. So that's in March the 22nd, something around that date. It changes slightly. But around that point, the length of the day is about the same as the length of the night. We get about 12 hours of daylight and about 12 hours of nighttime. And so that's where the word equinox comes from. Equi equal, nox, night. And so that imaginary point on the celestial sphere, out in that direction there, is just called the first point of Aries. The first point of Libra is its cousin on the other side of the Earth. It corresponds to the other equinox, the autumnal equinox, the September equinox here. And that's just the opposite side. So a star that is sat on the first point of Libra, I don't think there is a star there, but a star that would be sat on the first point of Libra would be 180 degrees around in both directions from the first point of Aries. So what do we call those directions? Well, the direction left and right around from that point we call right ascension, and the direction up and down we call declination. So we have 180 degrees declination and 180 degrees right ascension from the first point of Aries is the first point of Libra. Here's just another diagram, but this time I switched them around. That's all I did here. And so here you can see how the first point of Aries and, in a minute, the first point of Libra correspond to that position in the sky. So this is a map of the celestial sphere. The ecliptic is marked off here. And so you can imagine we have our horizon going across the middle, our celestial horizon going down the middle. There's our ecliptic going this dotted line. And you can see that there are in fact 13 constellations that the ecliptic passes through. It's the usual ones in grey here, that's the Zodiacal Band. But then we've got this constellation here, and I won't embarrass myself trying to pronounce it, that also is on that ecliptic. And over time, due to libration, other things, this isn't going to stay the same. This is going to change. Now, the year these were discovered are listed on the top, and I'm not interested in those particularly. But what I am interested in is these points of declination and right ascension. So you can see here, 0 hours, we use hours as the unit for hours and minutes and seconds for right ascension. That's our sort of our prime meridian in the celestial sphere, and it's at the very edges of this diagram. And 0 degrees declination is where the ecliptic is crossing the celestial equator at that point. And we go up towards the celestial north pole in degrees positive, down towards the celestial south pole in degrees negative, and the right ascension is always moving, as you can see here, across, it says from right to left as you look across the night sky. If you look along the celestial equator, from right to left in hours. So halfway around is 12 hours. The whole way around is 24 hours, which is back to 0 hours. But just a little bit less than that, 23 hours and 59 minutes. You get it. So this point over here, which looks like it's in Pisces, is actually the first point of Aries, even though it's nowhere near Aries. Aries is here. And then we've got this map to show you where the first point of Aries actually is. It's going to be difficult to see, but I reckon if you squint and move really close, you'll be able to see that right in the middle here it says vernal equinox, and there's a little red X here. And this pale blue line that starts at the top here and goes down here is labelled celestial meridian. So that is your 0 degrees right ascension, and it increases in hours as you move from right to left. And then we have our declination, which is measured from 0 at this point, and it goes positive angle towards the celestial north pole and negative angle towards the celestial south pole. And so any point in that celestial sphere, you can say where it is. You can give yourself a coordinate of where it is. Remember I said the other side was the first point of Libra. Well, here it is. It's where the sun is in the September equinox, right in the middle of this diagram. Again, notice it's nowhere near Libra. That's because these things have changed over time from when this was first defined. But in the night sky, this is what it would look like. So here's a star map. And again, it's going to be difficult to see, but if you squint and move really close, you'll see there is the equinox with a little red X here. This meridian is labelled 12 hours. So that's the meridian exactly on the opposite side of the celestial sphere to the prime meridian. And just as before, we would have these horizontal-ish lines representing declination, where we go positive angle as we go north and negative angle as we go south. So this is a view of the northern hemisphere. If you stood on the North Pole, the geographic North Pole, and looked straight up, you would see the celestial North Pole here. And here you can see that the celestial meridian is down here. So somewhere along this line is where you'll find our 0 degrees, or 0 hours, should I say, right ascension. You'll see that Cassiopeia is quite close to it, so that's quite a handy way of being able to identify it. It's exactly the opposite side to Ursa Major, which has this familiar asterism here, commonly called the Plough in the United Kingdom. In the United States of America, they like calling that the Big Dipper, and I think that terminology is gaining popularity in this country. But it's part of Ursa Major. So we're going to move on to a fun game called What's That Object? You look up in the night sky and you see something and you think, what is that? Well, working from small to large, this is what it might be. If it's very, very small, about meter wide, less than a meter wide, we can call it a meteoroid. It's a bit bigger than that, we call it an asteroid. And a bit bigger than that, big enough that it's no longer an asteroid because it can be spherical, its own gravity is enough to pull it into a sphere, we can call that a dwarf planet. Now all of those three bodies are too small to, what it says here, clear their orbital neighbourhoods. What that means is similar sized bodies or larger bodies also exist in an orbit that crosses the orbit of these bodies in some place. So the Moon is not a dwarf planet because its orbit around the Sun, interesting orbit as it is because it's also orbiting the Earth, is about the same place. It's got the same orbital neighbourhood as the Earth. And the Earth is bigger than the Moon, so the Moon cannot be a planet. That's also true for things like Pluto, where Pluto's orbit crosses Neptune's, and so it doesn't clear its orbital neighbourhood of similar sized or larger objects because Neptune is in its orbital neighbourhood. And therefore, even though Pluto does go further out than Neptune, because its orbit crosses Neptune's orbit, it's not a planet. If you are going to define a planet as being purely what it is, not where it is, and you decided that Pluto would be a planet, then by my reckoning the Moon would also have to be a planet, which I don't have an objection to. So meteoroid, small rock up there in space. As it's falling through the Earth's atmosphere, you see it. That's a meteor, shooting star. And then when you find it on the ground after it's fallen through the air, that is a meteorite. And you have to know what these three different terms mean. Meteoroid is in space, meteor is falling through the air, meteorite on the ground. And different meteors, sometimes you see them as a single object just moving very quickly across the sky, like this picture here. Sometimes you might see it moving a bit more slowly, like this picture here. This picture on the right is something of an exaggeration. That is not a meteor shower that I've ever seen, but you might see perhaps one every half a minute on average, or maybe one every minute on average. If you sit there and gaze at the sky for long enough, that's a meteor shower. That's more than one or two. That's one every half a minute, every minute, every 2 minutes. You consistently see them. Maybe you see 30 across the space of an hour. That's a meteor shower. And we get a few of those every year. Now this is a lovely video clip which I'm going to show you of just how energetic these meteors can be. So this was quite a large meteoroid in space which then entered the Earth's atmosphere. A few years ago now, 2013 this video was taken. And this made the news. This was a dash cam somewhere in Russia. And if you look to the top left, you're going to see that there is an object coming in. There it is. Now, as this object entered the Earth's atmosphere, it had so much energy, you can see it's actually casting its own shadows. The explosion shattered windows. It was huge. You know, this obviously caused a little bit of panic when it was first seen, although you wouldn't be able to tell it by looking at this video. But this particular type of meteor we call a fireball. If it's that bright, We call it a fireball. It's got a special name. Now, what you'll notice on this quick little animation is that, well, obviously the Earth is rotating, so you can see the background stars moving, but can you see the meteors tend to come from somewhere here? They all tend to stream away from some point. It's hidden behind this structure here, but there's some point in space that appears to be radiating out these meteors. And that point's got a special name. It's called the radiant of a meteor shower. And one of the practicals you can do, the observations you can do for your GCSE, is identifying the position of a radiant. And so the way you can do that is by getting a star chart like this. Maybe you've got a star chart that you can print off that has other stars, well-known asterisms on it to help you with this. And you simply mark off where the meteor starts to be visible and stops being visible as best as you can by looking up at the night sky, lying back in a comfortable chair with your piece of paper in front of you and your pen. And you're looking and you say it started there, it finished there, and you mark it off, started there, finished there, and maybe you number them so you know which 2 points correspond to each other. And after a few hours outside staring at the sky, you connect all those lines and you see where they originated from. And you see there it is, there's the radiant. So what causes there to be a radiant? Radiant's caused when the Earth moves into the path of where the asteroids are. One source of asteroids is the debris left over by comets. So you can see in this diagram a comet has moved very close to the sun as it's orbited and it's left its debris behind. As the Earth moves through that debris field, moving into that debris field, it passes through it, and asteroids are going to, which have been left behind from the comet, are going to enter the Earth's atmosphere. So the last thing we're going to look at is a few specialist terms that you may hear referring to how planets can appear in the night sky. And it's best summed up with a diagram like this. Somehow you've got to remember most of this diagram, not all of it, but most of it. For example, the terminology superior planet orbit is just any planet that's further away from the sun than the Earth is, and an inferior planet is any planet that's closer to the sun than the Earth is. Then we've got some other terms, like this term down here. Opposition is when the object we're looking at, the planet, which has to be a superior planet, is exactly the opposite side of the Earth than the sun is. That's opposition. And then we have conjunction when that superior planet is exactly behind the sun compared to where the Earth is. That's conjunction. Now, an inferior planet has two different conjunctions. It has an inferior conjunction when it's between the Earth and the sun, and it has a superior conjunction when it's the other side of the sun, behind the sun. And then we have elongation. When you have elongation, you have a right-angled triangle formed between the Earth, the planet you're looking at, and the sun. So there is your elongation. We've got western and eastern, but it doesn't matter. There's your elongation there. So it's conjunction, opposition, elongation. And you can see those on that diagram. Conjunction to the other side of the sun, or between the sun and the Earth if it's an inferior conjunction. Opposition, it's the other side of the Earth to the sun. And elongation, 90-degree angle. Two more technical terms. Transit is what we say when a body moves in front of another body. So, for example, this is a transit of a planet in front of a star. Maybe this is Venus moving in front of the sun, or, well, given the size of this, I don't think that's the case. But you can get things like the transit of the International Space Station in front of the sun, and astronomers get very excited about that sort of thing, get out their pinhole cameras or their amateur telescopes set up with special filters projecting onto screens so they're not looking into the telescope whilst looking at the sun. That would be very, very dangerous. And they get beautiful pictures of transits. The other one you need to know about is what we call occultation, which is where one body is hidden behind another one. So here the body on the right is occulting the body on the left. It's hiding a bit of it. A bit like an eclipse. And so those are all the technical terms you needed to know. We've gone through all those key points now. So what I'm going to ask you to do is leave a comment if you're not quite sure of anything, or if you want me to go through anything again, please do. Please do consider liking and subscribing to the channel so you get updates when these videos go live. Like the video, that helps me with increasing my reach. And I hope you've enjoyed it. Tune in next time for the next video.